Okay, the next part of section 813 is example 8-8. It's very similar to example 8-7, except that now we're going to incorporate an inductor into the load. So it will be, each load will be a series inductor and resistor. And let's see how that changes our approach to the problem. Just a slight complication. This problem is asking us to find the current in each line. So we're looking to find the current in each load. We're going to find it in one. We're going to realize that it is, the same for each balanced load. We're also going to initially recognize that this is connected in Y because each load has a common connection point. And the way that we're showing this in the textbook is the most efficient way to draw these this arrangement of these components. Okay, so find the current in each line is part A, and find the voltage across in each inductor terminal. Now, a little bit different this time. We need to find the total impedance of each branch. Now, I hope you remember how to do this, but for the total impedance in each branch, Z is equal to the combination of the resistor and the inductor. So for this particular one, that would be 3 squared plus 4 squared. This written in another way, right? This is, we're looking at this value, this form of this. This is, a combination of impedances. So that's what we're working at. That's what we're trying to figure out here. We can't add them directly. They have to be added as vectors, right? So that's why we have to do that this way. Okay, so that ends up being 9 squared plus 16 . Okay, square root of 25 is 5. Okay, so the total Z for each branch is 5 ohms. I am connected to 440 volts. That is the voltage. That's a line voltage. That's from there to there. That's from there to there. And it also would be from there to there. Okay, so that's where that comes from. Now, I want to know the voltage across each branch. The best way to do that is to go back to my equation that I had earlier, that the line voltage is equal to the square root of 3 times the line to neutral voltage. Line to neutral voltage, because if we know what the voltage is from here to here, right, then we can figure out what we're dealing with and make these current and other calculations with it. So line to neutral voltage would be line voltage, which is 440, divided by square root of 3. That's going to be 440 divided by square root of 3. And that is going to come out to be 254 volts across there. If I have 254 volts across there, the current will be 254 volts divided by the impedance in that branch, which is 5. So the current in each branch is 50.8 amps. I got something turned on here that's making shapes for me that I don't really want. 50.8 amps. So I have 50.8 amps in here. I have 50.8 amps in here, and I have 50.8 amps here. Now, the next part of this says that I need to know the voltage across the inductor. Piece of cake, right? Voltage is equal to current times resistance. Voltage is equal to 50.8 times 4 ohms, right here, right? And that's going to come out to be, 203.2 volts. So if I looked at one of these, that would tell me that across that inductor, the voltage is 203.2 volts. Same for this one and all of them. And that is how we would solve that problem. Okay? So again, here we are working problems. Here we are working problems using things that we've known all the way back from first circuit analysis course, incorporating other aspects of what we've learned recently, taking a three-phase circuit and solving it one branch at a time and coming up with the correct answers.